Welcome back, everyone, to our lecture series for Math 1210 Calculus 1 at Southern Utah University. As always, this is your professor, Dr. Andrew Misseldine. Good to have everyone here today. So this is lecture 37 in our course entitled Curve Sketching 2. This lecture is intended to be a continuation of what we talked about last time in lecture part 36 about curve sketching. The examples for this lecture will be taken from James Stewart's calculus textbook, particularly section 4.5 entitled Summary of Curve Sketching. And so in the last lecture, we talked about the basics of curve sketching and we worked through 3 examples. And that took a good honking 50 minutes to get through them all. One curve sketching example can take a lot of time. So I want to do some more examples, 3 more this time. It shouldn't take as long because we're not learning the basics of it this time. But I want to do some more examples. Last time we had focused entirely on functions that were polynomials or rational functions, that is, quotients of polynomials. I wanted to look at some which were a little bit more exotic today. So for example, let's take this function f of x equals x squared over the square root of x plus 1. That is, there's a square root involved in the calculation this time. How does that affect things? Well, if we start off looking at the domain of this thing, the issues with the domain are going to come from the denominator, because we don't want to divide by 0 and we also don't want to take the square root of negative. So if we think about the square root issue first, we need that x plus 1 is greater than or equal to 0, which would suggest that x needs to be greater than or equal to negative 1. But likewise, we also don't want to divide by 0, in which case the square root of x plus 1, we have to figure out what makes that equal to 0. Well, squaring both sides, that implies that x plus 1 equals 0, or in other words, x would equal negative 1 there. So earlier we had mentioned that x should be greater than or equal to negative 1, but here, because of division by 0, we actually don't want it to equal negative 1. So the domain of this function is going to equal negative 1 to infinity, where negative 1 is not included in that. I also want to mention that right off the bat, that if its domain is negative 1 to infinity, we can already say that in terms of symmetry, there's not going to be any symmetry here. You can't be even or odd if your domain isn't symmetric. Therefore, I'm not even going to bother calculating it because I know it's not going to work. In terms of intercepts, right, if we were to look at f of 0, we would get 0 squared over the square root of 0 plus 1. That gives us 0 over 1, which is 0. It's our y-intercept. And then if we were to try the x-intercepts, we have to look at x squared over the square root of x plus 1 equals 0. Whenever a fraction equals 0, you can really just multiply both sides by that denominator. It cancels out. It's only the numerator that matters in this situation. X squared equals 0, and then we get that x equals 0. So what we've discovered here is that our x-intercept is also our y-intercept. It's going to be 0, 0, and the domain is going to be negative 1 to infinity. So let me highlight sort of the important things we found here. So we have an x-intercept and a y-intercept, and our domain was given. Great. Let's consider the end behavior of the function. So if we take the limit as x approaches infinity here of our function x squared over the square root of x plus 1. As x goes to infinity, let's again pay attention to the dominant terms going on right here. In the denominator, the dominant term is going to be the square root of x. In the numerator, it's going to be an x squared. And so this thing is going to look essentially just like x squared over x to the 1/2 power as x goes to infinity. And so this would simplify as a fraction just to be x to the 3/2 as x goes to infinity. And so as a power function, as x goes to infinity, some positive power of x will also go to infinity. So this thing points up on the right-hand side. But on the left side, things are a little bit different. We can't ask the question, what happens as x goes to negative infinity, because this graph terminates at negative 1. So we can actually ask what happens as you approach negative 1 from the right, as we get x squared over the square root of x plus 1. And so what happens as x approaches negative 1 right here? Well, on the top, you're going to get negative 1 plus squared over the square root of -1 plus 1. And so when you square something, it's always going to be positive, and so the -1 is just going to look like a 1 on top. Now we have to be careful on the bottom, because if you're approaching -1 from the right and you add 1 to it, is that going to be a positive number or a negative number? And it's going to be positive, because we're a little bit shy of -1 from the right. When you add 1 to that, that'll give you 0 plus on the right hand side. We take the square root of that. Well, that'll simplify to be 1 over 0 plus, which looks like plus infinity. So it turns out that this is going to give us a vertical asymptote on the graph, and we're going to point up on the right hand side as well. So let's record what we have so far on the graph. So we know that this function will go through the origin. It's its x and y intercept. We know that on the right hand side it wants to point up. Maybe I do a different color for that, because we'll have to come back to this in a little bit. We know it points up on the right hand side. We also know how to vertical asymptote at x equals -1. So let's draw that. And so we also can see that this thing is going to be pointing up on the right hand side. We'll come back to those a little bit later. Let me erase them for now. All right, so let's think about the derivative for a little bit. How is the derivative going to affect things? Well, the original function, let me write it back on the screen so we can see it here. The original function y equals x squared over the square root of x plus 1. Let's see, x plus 1. And so as we look at the first derivative, we're going to have to apply the quotient rule again. And I'm not going to go through all the details of calculating the derivative this time, just so you're aware. But if we take the derivative, we're going to end up with 3x squared plus 4x over 2 times x plus 1 to the 3 halves, like so. All right. And so there's some details to be there, and I apologize for not doing all the details there, but that's going to be the usual quotient rule type of thing. And so what we want to be looking for is, when does this thing go to 0? That'll happen when the numerator goes to 0. So we're interested in 3x squared plus 4 equals 0. If you factor that thing, you can take out a factor of x. So you get 3x plus 4. When does that equal 0? And we can see that this will happen when x equals 0 and -4 thirds. We also have to worry about when the denominator goes to 0. And the denominator is going to go to 0. The 2 doesn't make much of a difference. The denominator will go to 0 when x plus 1 equals 0, which happens here at -1. Now, -1's outside the domain of this thing, so nothing's really too worried about right there. We need the second derivative, which again, you're going to excuse me, I'm just going to jump immediately to the derivative. Use the quotient rule again on this thing above. And when you take the second derivative, you'll end up with a 3x squared. Right, 3x squared plus 8x plus 8. And this sits above 4 times x plus 1 raised to the 5 halves power. And so again, there's issue. The denominator will go to 0 when x equals -1. That's the boundary of the domain. When does the numerator go to 0? Well, the denominator won't make much of a difference there. We have to look at the denominator there, the numerator there, excuse me. So we have 3x squared plus 8x plus 8. When does that equal 0? And when you try to solve this quadratic polynomial, you could try to factor. It doesn't really work. You could use the quadratic formula, but it turns out that when you try to solve for this, it turns out it never actually equals 0. This thing is strictly positive. And so this tells us that the graph has no PPIs. It'll be either always concave up or always concave down. Let's come back up here. And so if we build our sign chart, the numbers that we should be interested in from what we looked at before, the second derivative never equal to 0. We had a single critical number at 0. And actually, I forgot to mention this earlier, because didn't we have two critical numbers, right? We had 0 and -4/3. But remember the domain, right? The domain was -1 to infinity. -4/3 is outside of that domain. So we only have the one critical number at 0. So that's all we have to contend with when we look at the second derivative here. Now the second derivative, remember what it was, is the 3x squared plus 8x plus 8 was always positive. The 4 is always positive. And x plus 1 will be positive when you're greater than -1. And it'll be 0 when you're less than -1. And so what we see is that the second derivative is always positive right here. And so this graph is going to always be concave up. Concave up, concave up. And so we actually get a local minimum right here on the graph. So x equals 0 represents this minimum value. If we approach our asymptote, we're going to go up towards infinity. And then we're also going to approach infinity on the right-hand side as well. And so the graph's going to look something like this. Let's take a look at a computer-generated image, and we see, voila, we had a pretty good picture there. All right, as a next example, take the function f of x equals the natural log of x over x squared. In terms of the domain, what issues do we have to worry about? Well, when it comes to the natural log of x, the input number x has to be greater than 0. And in the denominator, we can't have x squared equaling 0, which would imply that x equals 0. But as the natural log already thinks that x should be greater than 0, we get that our domain is going to be 0 to infinity. Right there. I'm going to circle it so we see that. If we switch our attention to x-intercepts and y-intercepts, I should say, the y-intercept doesn't exist because, after all, if x can equal 0, that's exactly where the y-intercept is. So there's no y-intercept. If we think of it in terms of the x-intercepts, when does the natural log of x over x squared equal 0? Timesing both sides by x squared, you get that when does the natural log of x equal 0? And using the inverse function relationship here, the natural log of x equals 0 implies x equals e to the 0, aka 1. And so this gives us our y-intercept, x-intercept. We have a single x-intercept right there at 1. In terms of discontinuities, the only discontinuity we'd have to worry about would be when x goes to 0, because that makes the denominator go 0, but that's already outside the domain. So I guess there's an issue about what happens as we approach 0. That basically leads us automatically to the end behavior, right? What happens as x approaches, say, 0 from the right, the natural log of x over x squared. And so if we investigate this one, what's the natural log of 0 from the right over 0 plus squared? Well, the denominator is pretty simple. If you square a positive, it stays positive. So we're going to be just a little bit to the right of 0, 0 plus here. The natural log, as x approaches 0 from the right, the natural log wants to go towards negative infinity. And so we might be worried, is this an indeterminate form? Well, if you divide by 0, that's kind of like the same thing as multiplying by infinity. So this really looks like negative infinity times positive infinity. And that's actually not an indeterminate form whatsoever. That would just be negative infinity. And so this will represent a vertical asymptote on the graph. That is, as you get closer and closer to 0, you're going to be approaching negative infinity. We also should see what it does on the right-hand side. As take the limit as x approaches infinity, the natural log of x over x squared. Now in this situation, if you just plug in x equals infinity here, you're going to get the natural log of infinity over infinity squared. This one actually does have an indeterminate form, infinity over infinity. So to resolve this one, I would recommend using L'Hopital's rule, for which we can take the derivative of top, which gives 1 over x, and the derivative of the bottom, which is 2x, as x approaches infinity still. Simplifying that fraction, we're going to end up with 1 over 2x squared as x goes towards infinity. And in that situation, we're going to end up with 1 over infinity, which is 0. So this function has a horizontal asymptote at the x-axis. All right, the remainder of what we need to talk about comes from the derivatives. So let's compute the derivatives of these things. I still feel pretty awful what I did earlier, just skipping through the derivative. We should do the calculation. All right, we can do it. Those steps I did skip before, you can find them in the lecture notes. But let's do the quotient rule this time. So we get low d high minus high d low, square the bottom. Here we go. And so factor the top. We'll simplify things first, I guess. X squared times 1 over x is just an x. We get minus 2x times the natural log of x over x to the 4th. You can factor out the x that's in the top, and that leaves behind 1 minus 2 natural log of x over x to the 4th, for which we can cancel the x on top with one of the x's on the bottom. And so we get 1 minus 2 natural log of x over x cubed. We want to remember this guy right here because we're going to have to take the second derivative in just a moment. But in the meanwhile, let's think of the critical numbers. The denominator goes to 0 when x is 0. We already know that's the boundary of the domain. When does the numerator go to 0? 1 minus 2 natural log of x. We solve this equation right here. We can add 2 times the natural log of x to both sides. So we get 1 equals 2 ln of x, which would tell us the natural log of x equals 1/2, or x equals e to the 1/2 power, or if you prefer, the square root of e. And let's see, the square root of e, that's approximately, I should have put this in my calculator beforehand. This is approximately 1.65 for future reference. Let's compute the second derivative. If we take the derivative of the function we had before, again, we can use the quotient rule to help us along the way. So we get low d high, the derivative of 1 minus 2 natural log of x would be negative 2 over x minus high d low, square the bottom. Here we go. So we get x to the 6th in the bottom right here. And then trying to simplify this thing along the way, x cubed times negative 2x will give us negative 2x squared. We get this negative 3x squared times 1 minus 2 natural log of x all over x to the 6th. So factor out the negative x squared that's common to the numerator. Whoops, sorry about that. And then that leaves behind, what do we got? A 2 plus 3 times 1 minus 2 natural log of x. And this sits above the denominator, which is x to the 6th. So we can simplify the denominator a little bit. We get x squared canceled there, leaving 4 there. What's going to happen in the numerator? We're going to have 3 times 1, which is 3, plus 2, which is a 5. So we get negative 5. And then we're going to get a negative 6 natural log of x sitting above x to the 4th. So the PPIs here, again, the denominator will go to 0 at 0. The numerator will go to 0 Well, in that situation, you get 5 minus 6 natural log of x equals 0. Very similar to what we did a moment ago, we're going to get the natural log of x is equal to 5/6. And so our PPI, I should say potential point of inflection, we don't know it's an inflection point yet, it's going to be e to the 5/6 power, which is approximately 2.3. So let's try to graph those points right here. Now our critical number was 1.65, the square root of e. So we get this point, well, we had an x-intercept. Let's do that one first. The x-intercept was at 1. The critical number is going to be 1.65 approximately. If you plug it into the function, you're going to get something super, super teeny tiny. If you put that into the function, you get a 0.18. So in terms of scale, let's actually make the y coordinate be just 0.1, 1/10 right there. And so when you look at the y coordinate, this thing is just going to be a teeny little guy right here. So we get this point 1.65, comma, what did I say, 0.18? Super small. And then for our point of inflection, we got e to the 5/6, which was about 2.3. If you plug that into the original function f, you're going to get 0.16 as the y coordinate. So what did I say? 2.3. So we graph that. It's going to be about right here. 2.23, or 2.3, excuse me. And then 0.16. That guy's not very big whatsoever. And so we know we have a vertical asymptote at the x-axis, at the y-axis. We have a horizontal asymptote at the y-axis. And if we fill out our sign chart here, so we're looking at 1.63 and 2.3. If we look at the second derivative, which is off the screen right now, come back up. Our second derivative was this thing right here. The denominator is always going to be positive. There's a negative in front. This thing will be negative until it hits its x. I'm sorry. This thing should be, yeah, this thing will be positive until it hits its x-intercept, and it'll switch to be negative. But because of the negative sign, it actually switches things around. So if we were to plug these into our function right here, into the second derivative, it's going to be negative, negative, and then positive. And so what this tells us is that we have a point of inflection. It's going to be concave downward, like this, going towards negative infinity. And then at this point, it's going to switch to be concave upward as it approaches the horizontal asymptote, which is the x-axis. So this gives us our graph right there. Looking at a computer image, we get this picture right here. So notice that this point is an inflection point. It's concave down right there. It's concave up right there. This point right here is a maximum. It was increasing, then decreasing. You see the asymptotic behavior as it approaches the x-axis. You see the asymptotic behavior as it approaches the y-axis there. All right, let's look at one last example. Let's do one with a little bit of trigonometry to it. That'll be fun. So what should we know about here is that the domain, right? The domain of cosine is all real numbers. The domain of sine is all real numbers. So the only issue is the denominator. If you look at the denominator, 2 plus sine of x, does that ever equal 0? Well, subtract 2 from both sides. You get sine of x equals negative 2. And I'm going to stop you right there. Sine has to sit between negative 1 and 1, positive 1. It can never equal negative 2. So what we actually get is that its domain is going to be all real numbers. But unlike the other graphs we've seen, sine, or this function is periodic by the nature of the trigonometric functions here, right? And so it's going to be, in fact, periodic on 2 pi. Because cosine repeats itself every 2 pi, sine repeats itself every 2 pi. If we can just graph it on the interval pi, or on the interval, 2 pi, from 0 to 2 pi, we could be just fine. Absolutely just fine with that. So we can do something like that. Let's see, what else do we need to talk about? So the next thing to do, we can think about intercepts. Think of intercepts. What would the y-intercept be? F of 0 equals cosine of 0 over 2 plus sine of 0. Cosine of 0 is a 1. Sine of 0 is a 0, so we get 1/2 as our y-intercept. In terms of x-intercepts, you get cosine of x that sits above 2 plus sine of x. When does that equal 0? Well, to find an x-intercept, it only matters what happens in the numerator. Cosine of x equals 0. And think about our standard trigonometry. Cosine will equal 0 exactly at, let's see, at pi halves. Right, cosine's equal to 0 at pi halves, but also at 3 pi halves, 5 pi halves, and it will repeat itself again, it's periodic in the nature there. We're going to get x-intercepts over and over and over again. In terms of discontinuities, cosine, sine are all continuous. The only way there could have been a discontinuity is if we divided by 0, but like we said earlier, that's not a possibility. It was periodic. We already talked about the symmetry there. So let's talk about end behavior. Well, for periodic functions, there really is no such thing as end behavior because it just repeats itself over and over and over and over, and wait for it, over again. So asking the limit as x goes to infinity versus negative infinity, that's not going to give us any information there whatsoever. So we can actually jump directly to our derivatives. Let's calculate the first derivative by the quotient rule. You can see the quotient rule is our best friend in this section. By the quotient rule, we get 2 plus sine of x times the derivative of cosine, which is a negative sign. Do make sure you put parentheses there so you make sure that you're taking the correct multiplication there and you don't accidentally subtract it. Then minus cosine, oh, I should have planned ahead here, times the derivative of 2 plus sine, which is a cosine. And this all sits above 2 plus sine x squared. Don't multiply out the denominator. Let me move down to give myself some more room. And so if we distribute the negative sign onto these two pieces right here, we're going to end up with a negative 2 sine of x. We're going to have a negative sine squared. And then we also have a negative cosine squared. And this sits above 2 plus sine x squared. Now, since everything in the numerator was divisible by negative 1, I'm going to factor out that negative 1. And so we get 2 sine x. And now my trigonometry sense is tingling, right? You look at things like sine squared and a cosine squared. We know this comes together to give us 1. This is the Pythagorean identity. So we're going to get 2 sine of x plus 1. And this sits above the 2 plus sine of x. Now, despite the fact you see a 2 on the top and the bottom and a sine on top and bottom, there's no cancellation that goes on there. This is our simplified derivative. To find the critical numbers, we look at what makes this thing equal to 0. And in which case, we set 2 sine of x plus 1 equal 2 sine of x plus 1 equal to 0. This gives us sine of x equals negative 1/2. And so think about those unit circle diagrams that we've known from the past, if you have to. When does sine equal 1/2? This will happen in the first quadrant and in the second quadrant. The first one will be 30 degrees, which you can repent of that and switch it to radians if you need to, right? Which case we should then get, I'm sorry, it's going to be a negative 1/2, isn't it? Because I forgot something, didn't I? Let's just pause for one moment because we have a negative sign right there. That shouldn't make any bit of a difference. We factor out the negative out of everything. I'm trying to make sure I did make a calculation error anywheres. Oh, okay, I did make a mistake somewhere. Oh no, it was right. I'm sorry. We see right here we have sine as negative 1/2. So let me actually try this unit circle argument one more time. We're not interested in when it's equal to 1/2. We're interested in when it's equal to negative 1/2. So that's actually going to be below down here. So we're talking about an angle in the third quadrant and in the fourth quadrant. So this will reference to 30 degrees. We're actually looking at x is 7 pi sixth, and also 11 pi sixth. Now it'll repeat itself, but this will give us the critical numbers in a single period. And so let's then take the second derivative here. If we take the second derivative, again, there is a calculation going on here. For the sake of time, I think I'm going to skip over it. The details can be found in the lecture notes here, but if you take the second derivative by the quotient rule again, you get 2 times cosine of x times sine of x minus 1. And this sits above a 2 plus sine of x, and then the denominator is cubed. All right, so the PPIs here are going to be the things that make the numerator go to 0, because there's nothing in the denominator will make, there's no choice of x that makes the denominator go to 0. So we have to worry about, when does cosine go to 0? All right, when does cosine go to 0? And we mentioned that before. Those are our x-intercepts. Those happen at pi halves and 3 pi halves. But then we also have to worry about, when does sine of x minus 1 equal 0? That would happen when sine equals 1, which would happen at pi halves. Like so. And again, this repeats itself, but this gives us all the critical numbers for a single period. Did I forget anything there? No, I think we're good. And so now let's build a sine chart using these critical numbers and these PPIs. I'm going to put it below our picture right here. So there was a lot of stuff. Let's keep track of it here. And so what do we have to worry about? So we we're going to do one period. So from 0. So we had a PPI at pi halves. We had a critical number at 7 pi sixth. We had a PPI at 3 pi halves. And then finally, we had another critical number at 11 pi sixth. All right. And then this then stops itself at 2 pi. It'll repeat itself, but that's all that we have to do. We're going to get tons and tons of solutions otherwise. And so if we come to the second derivative, let's take a look at it again real quick. Our second derivative, this might be a useful situation to use test points where you plug in specific numbers in these intervals right here. You can always use the factorizations of these things, but however you want to do it, there's ways to do it. You're going to end up with, you get a negative between 0 and pi halves. You get a positive between pi halves and 7 pi sixth. You're going to get a positive between 7 pi sixth and 3 pi halves. You get a negative between 3 pi halves and 11 pi sixth. And you get a negative again from 11 pi sixth to 2 pi. And so what this tells us right here is that we have a point of inflection at pi halves, a point of inflection at 3 pi halves. We have a local minimum at 7 pi halves, and we have a local maximum at 11 pi sixth. And so let's try to put all this information together. So we had intercepts at pi halves and at 3 pi halves. We had a inflection point at 7 pi sixth, which is going to be right here on the graph. And then we had another inflection point at 11 pi sixth, which is almost 2 pi. Right here. So here's our 2 pi. Here's our 0. And so if we connect the dots, our y-intercept before was 1/2, wasn't it? So if we connect the dots, we're going to get this one right here. So let me kind of explain what's happening here. You get an inflection when you are between 0 and pi halves. It should be concave up. When you're between pi halves and 3 pi halves, it should be not 3 pi halves. No, that's right, 3 pi halves. you should be concave upward again. I'm sorry, I said concave up before when I meant down. Let me fix that. This is concave down right here, concave up, and then concave down again. We have a maximum right here. Sorry, this is a minimum. We have a maximum right here. And this is what the picture is going to do, and it'll replicate itself over and over again. It'll just, and in this, because the blue one just gives us one period, and it just kind of repeats itself over and over and over and over again, like so. And this will be repeat. And so if we look at a computer-generated image, we see exactly this. The one in yellow is the period we first started off with, and the one in green then gives us the what it looks like over and over and over again. And so the examples in this one were much more challenging than the last lecture, and I do understand that, but if you're patient with yourself, you can get some really accurate drawings of these curve sketches. And that actually concludes our lecture for today. If you have any questions, feel free to post them down in the comments below. There is a link to the lecture notes for this lecture in the description below. Feel free to use those in your studies. See you next time. Bye.